All right, I think it's time to get started. Hello, everyone, and thank you for joining us today in this PROFINET Network Design webinar. I am Nelia Young, Technical Marketing Director of PROFIBUS and PROFINET North America. I am joined today by Hunter Harrington, Consulting Engineer at the Profi Interface Center, a Competence Center, Testing Lab, and Training Center for PROFIBUS and PROFINET here in North America. A few details before we get started. First, all the video recording and the slides will be uploaded to the PI North America website. I'll call it being here if you register for the webinar, but you can find all this information later today at us.profinet.com/training/webinar. Also, we'll be covering quite a lot of material today. Feel free to send us any questions through the chat. We'll be answering all the questions at the end of the webinar, but it will be beneficial for us to be able to have those questions ahead of time. We'll get started with this presentation by learning a little bit more about the PROFIBUS and PROFINET International Organization. PI, or PROFIBUS and PROFINET International, is the creator, maintainer, and promoter of open industrial communication standards, such as PROFIBUS and PROFINET. It was founded in 1989, and everything started with PROFIBUS. A few years later, as the industry shifted into industrial Ethernets, we also shifted into PROFINET. Some years passed, and then we saw a necessity for more sensors and actuators technologies, and that's when we added IO-Link. To be able to fulfill the mantra of PI of assisting and educating users around the world, we have many sub-organizations that helps us fulfill this mission. Some of those organizations are regional PI associations. These are PI associations around the world, such as PI North America, PI Netherlands, PI Japan. So anywhere in the world where you are located, or maybe where an installation would be located, you'll have assistance locally. We also have competence centers, which are exactly that, centers of competence, where you have PROFIBUS or PROFINET expert to help you with your applications. We also have test labs, where products will get certified before going to market. We have training centers, if you're interested in getting some more in-depth workshops, training, or maybe even certified training. We have many of those around the world. Me, myself, I'm part of PI North America, which is one of those regional PI associations. We were founded in 1994, and if you have been familiar with us for many years, you may know us as the PTO, or the PROFIBUS Trade Organization. A few years later, we actually rebranded as PI North America. We're a member-supported, nonprofit organization, and within our area, the North America area, we also have many organizations that support us, such as competence centers, testing centers, and training labs. We have the Profi Interface Center, Phoenix Contact Software, Jacom Automation, and HMS. Now I'll be going over a brief introduction to PROFINET. Before we get into all the design topics, I was thinking it would be good to get a little bit of a refresh of how PROFINET works and what is PROFINET. PROFINET is the leading industrial Ethernet standard. It is a globally established and future-oriented technology suitable for factory, process, and motion control applications. Actually, a key factor is the large number of install-based PROFINET devices that we have currently. We hope this webinar can help current users of PROFINET and others thinking in starting a new project with this technology. PROFINET exchanges data between controllers and devices. To be able to do so, PROFINET uses 3 communication channels. We will cover more of these in just a little bit. We also mention in this slide some profiles, ProfiSafe, ProfiEnergy, and ProfiDrive. We won't be covering profiles in this presentation, but we do encourage you to look into that if you are interested. PROFINET is suitable for a large range of applications, all the way from standard communication to factory automation and to motion control. From these three communication channels that we just mentioned, the first one is the IP protocol for non-time critical tasks. The second one is the real-time channel for time critical tasks. And the third one is an isochronous real-time channel or IRT for the most demanding applications, such as motion control or drives. I'll go over each of these in a single slide so you can get a little bit more of information, starting by the non-real-time traffic channel. In the non-real-time channel, PROFINET transmits messages with TCP/IP or UDP/IP, which, as we expect, are large in size. This channel is used for parameterization, configuration, diagnostics, or other non-time critical tasks. This channel has lower priority than the real-time or IRT channel. The PROFINET real-time channel, or RT, has higher priority. It is also a lot faster, with cycle times that go down to 1 millisecond, and its real-time capacity makes it suitable to handle more than 80% of automation applications. Each controller, device, and application have their own cycle, which is non-synchronous. But this is not really a limitation for most applications. It is only a limitation for the most demanding, maybe motion control applications, which for that we have PROFINET isochronous real-time channel. The third communication channel actually is the highest performance. The cycle times in this case go down to 31.25 microseconds and have a jitter of only 1 microsecond. All communication is synchronous. We have fast and deterministic Ethernet through bandwidth reservation and scheduling. But again, most applications would be handled with PROFINET real-time. This is just for those most demanding applications that may need this high amount of speed and determinism. In conclusion, PROFINET uses those three communication channels to be able to transmit data efficiently and with the required speed and determinism. But most importantly, our protocols can also coexist in this single infrastructure with PROFINET. Since PROFINET is based on standard and modified Ethernet, we also have the capacity to have other Ethernet protocols running on the same wire, on the same network. I hope that was enough of a brief refresher on how PROFINET works. This material will help us get into more detail in the part of design, especially in the part of device selection. Today, we'll be covering these 5 network design topics. We'll be starting with device selection, and we'll be ending actually with the last section of resources and Q&A. So you'll have some time to ask us some questions and have a little bit of a conversation. Most of the content that we'll be presenting is based on the PI design guidelines. If you follow the URL here on the screen, you'll be able to not only download the design guideline, but we also have an installation guideline, functional earthing and shielding, commissioning guideline. All of them are free and you are able to download them. To make this presentation a bit interactive, we have added a couple of polls. If you could please answer them, it should be able to pop in your screen. The poll is open right now. If you could please select which is the most common design failure you encounter. As right now, you can only pick one. I'm sure you have encountered several of these, but please focus on the most common. We appreciate your feedback. We're actually going to use these results to be able to produce more collaterals that address the potential causes of these issues or build up on more material regarding to these. I'll give you a few more seconds. If you could please submit your answer. All right, I got most of you. Thank you. Well, now we can get started with this first item, which is device selection. If you are looking to build a PROFINET network, you have to start by looking at the individual components. And you may be familiar with so many different component types, such as IOs, PLCs, PACs, robots, motors, vision systems, switches, firewalls, HMIs, wireless access points, so on. We can go on for actually a long time. But to be able to choose the right devices, the right components for the application, we have to be able to make a decision based on some decision criteria that we have listed here. The decision criteria that we'll be covering are conformance classes, timing requirements, device function, communication relations, connection types, and additional features and requirements. We'll be covering all these topics in this section, except for the last one, which we actually have allocated a whole section into those additional features and requirements. The first step for device selection is to produce a floor plan and initial design of necessary device placement based on machine or plant layout. In this simplified factory layout, we show 3 different stations, which could perform different tasks, such as, for example, molding, assembling, and packing. We also have even add a few vertical components right here. Even at early stages where you are just setting up the stations, you may already have in mind, you may already know that you may want to send some data later on vertically through the cloud or through the office environment. Even though right now we have divided into these different stations, we have to go a little bit farther. We have to consider first the conformance classes. In this graph, we show the 3 PROFINET conformance classes. Every PROFINET device is part of one of these classes. Being conformance class A, the most basic one, and conformance class C, the most advanced one. The main difference really relies from A to B is the SNMP support, which will help us get some SNMP statistics with SNMP standard tools. From conformance B to C, you'll be able to have that real-time IRT, real-time data exchange. So if we relate those conformance classes with the timing requirements, we can say that conformance class A, B, and C are able to use the non-real-time channel and the real-time channel. That is just a standard communication for PROFINET, those 2. But really, only conformance class C devices will be able to communicate through the IRT channel because they have that synchronous application. So if you do require that capability, you have to look for conformance C class devices. Another aspect to keep in mind is the component role. We're probably well familiar with the device to controller interaction, but I would like to point out that there are components that can be used as supervisor, either passively or just for specific purposes. Consider using a supervisor to read or write diagnostic information, parameters to a device, maybe assign IP addresses or station names, or maybe even troubleshooting your network in a diagnostics type of role. This may be a bit of a less crucial decision criteria, but consider what connection type is available in the device that you're looking into adding into your network. If they have connections available for copper, fiber, or if you may need a converter. Also, some I/O devices have wireless connections already built in, so that's something that you should definitely consider. As we discuss a little bit more about media type later in the presentation, I just wanted to show you a couple of slides related to cables. There's actually a wide variety of copper and fiber cables available of different types and for different applications. Such cables have to be 100 megabits per second or higher, but that's really the only requirement. We do recommend using cables that are listed as PROFINET compatible, just because that will clear all doubts that you'll be able to work for us. Choosing between copper or fiber, that actually just comes from your own decision and judgment. But consider these decision criteria that we usually list here, which are distance, cost, environment, bandwidth, and the special applications. And if you think a cable just won't do it, maybe you want to use a wireless HMI, an automatic guided vehicle, moving parts, or any related applications, you also have that wireless option. And we actually have a whole webinar just on wireless, so if you're interested in that, just send us a message through the chat. We'll send you the link for that webinar. Now with this information that we just covered, we can go back to that design diagram. We started fulfilling the first step earlier, and now we can go to the next level. We can actually define the conformance classes. Most of the applications will be conformance class B. That's why we have listed these stations as being conformance class B. We have part of this station that is conformance class C, as you can see, usually for motion control. And we have also added some specifics regarding to the media type. Most of the devices we have started planning for copper. We have added a fiber connection right here. We actually noted that there may be some EMI interference, and since fiber is immune to EMI, that'll be the best choice. And we have also added some wireless connection right here, possibly for these wireless HMI. Going forward, the next steps for design will be to define an efficient topology, decide for a closed or open system. In some cases, applications may require an isolated PROFINET network, but as you see in this example, and as you see in most cases, we have a network mixed with other types of devices and an open network. You may also need to account for the need of redundancy or high availability, decide on additional features such as safety, and continue building up into those additional features. We actually will be building up in all these subjects in the next sections. But for now, we actually want to end up this information by asking you a quick poll on what is the most important part of the design process. I'll pull out the poll like before. If you could please just give us your answer here. Again, we'll be using these to be able to gather some more information and build on more collaterals on the most common parts that you consider to be more important, and then we can produce more materials for you, more educational materials. right. I think we got mostly everyone have submitted their answer. Thank you so much for your feedback. I'll close it right now. We will continue building up on all of those topics, but for now, I'll be sending over the controls to Hunter Harrington, and he will take over for network design topology.
Thank you, Nelly, and welcome to today's design webinar from my side. The first topic I would like to cover is network topology. Let's take a look at typical topology aspects we should consider, and then we will follow up with some tips for designing your network. As we have shown here, the network topology results from criteria such as the location of the components and the machinery, as Nelly was showing you on the previous diagram we had. Also the distances between them, EMC and electrical isolation requirements. That's also very important. Conformance class requirements related to PROFINET, for example, if you're doing motion control or other special application requirements such as high availability systems for redundant controllers, redundant devices, or redundant networks. And finally, consideration of critical network points where there could be a lot of converging traffic causing high network load. Shown here is a picture of our PROFINET topology options. PROFINET can support whatever topology you need for your application, a line, tree, ring, or star cable topology. In addition, we also can support wireless as well if you need to avoid cables for convenience purposes, moving equipment like automated guided vehicles, or even special applications again, such as a slip ring application. Each type of topology we have on PROFINET or networks section may have advantages and disadvantages which should be considered in the design. For example, a star and tree topology, which are both very similar, have the advantage that if one node fails or on the branch or endpoint, it can be removed and replaced without affecting most of the other network nodes. However, if a main branch or switch fails, then the whole network could go down. Also, star and tree topologies require switches with larger capacities, more ports, and more cabling, which can add to the cost of your installation. Next, we have a line topology. And this is possible with PROFINET as most devices have a built-in switch, allowing you to daisy chain or do a direct run between your controller to the devices. An advantage of this, of course, is the cost can be reduced since external switches are now optional and there's less cabling overhead. Of course, one disadvantage of line topology is if a node fails in the line, the downstream nodes are affected and can no longer communicate. We also need to consider the line depth, and we'll discuss that further in an upcoming section. Okay. For some applications, a ring topology can be used. In this case, it is possible to maintain network operations even if one of the sections or nodes in the ring fails. Normally, you got to remember that on Ethernet, a ring is not allowed without special handling measures in place. So be sure to avoid loops when designing your network unless you have this type of capability. On PROFINET, these are optional features, and we call that MRP or MRPD, and would require all the nodes in the ring to support that function. And in addition, a disadvantage, I guess, to redundancy, of course, you have to plan for that, and it's going to require some additional cost and of course, configuration to install and set up. Okay, for motion applications, it's necessary to have all of your conformance class C devices, those IRT nodes, interconnected on the same domain and network section, because that section of the network is going to be truly deterministic and be clock synchronized. So the real-time clock needs to be able to pass between all of those nodes. Other RT or Ethernet nodes can also be connected on edges of that domain, but you can't, of course, have a RT node in the middle of that domain, or something like a Best Buy switch, because all of a sudden now it wouldn't be able to transfer the clock information. And of course, if an external switch is used in your domain, it would also have to support IRT. So you can see those red switches here in our picture. Those are IRT capable switches, so that means they also support conformance class C. And note, just as in the other one, we had all of our nodes in that ring. If we did a ring topology, in this case we also show we can do a ring, those would have to support the MRPD functionality for IRT. So IRT can be used in any of the topology modes except for wireless, because the timing requirements on wireless, you can't meet that. But it's typically used in IRT is typically used in line or ring topologies. Okay, so when it comes to network layout, there are some things you should keep in mind. For example, if you're using a line topology, the depth of the line and the traffic on that line should be considered to avoid delays or issues. Also, you should take a look at critical network sections where you have the possibility for high network loads. So one place that would probably be would be right here at the PLC, because at the PLC, that's where all of your traffic is going to be going in and out, because the PLC has probably the most PROFINET load, if you're talking about the PROFINET protocol, because all of the traffic is going to be going out of the PLC. Keep in mind, however, that usually the PROFINET telegrams are smaller because our IO devices are usually sending some minimal IO data, but there could be a lot of frames if we have a high, fast update time on our PLC. But we also have to consider other types of devices that could be on the network, such as HMIs, vision systems, PCs, which typically may not speak the PROFINET protocol directly, but they're probably using some form of TCP/IP communications. And when you're talking about TCP/IP, this could be, these kind of telegrams or streams could be thousands of bytes for one request, because that you can have a fragmented, types of requests, and you could request a lot of information. And if you're going through a line again, that would be a lot of traffic going through that line. So, critical points on your network here would probably be here at this point, here at this point, because we don't know what kind of traffic these systems are sending. So we probably want to look at that, at those critical points, and be mindful of the load caused by those standard Ethernet devices. And of course, be careful with our line topology. We're going to talk a little bit more about that in detail in the next section. And areas of traffic convergence. So again, that would be areas where you have a lot of traffic converging, maybe at some of these switches or at the controller. Now, one way to help this high network loading is to implement the shortest paths possible for your devices, which send a lot of traffic or stream. So again, the best way to get rid of that HMI sending thousands of bytes through this line is to move it up here at the top, closer to the actual controller it's talking to, or again, the vision systems or whatever. So instead of putting, right there, you want to move it closer. So if possible, connect it closer to your controller if it's talking to the controller. You can also use multiple controllers or switches on your network to distribute the traffic across separate sections. Okay, so to finalize this section, we have some topology design tips for you across the next few slides that I wanted to talk about. The first tip is to consider the distances and ensure that you are not going over the limits on the cabling or through bulkhead connections, as that can increase your attenuation, causing intermittent connection loss or bad connections. I don't know how many times I've seen some electricians go out there and install some cable, and they kind of loop it in the cabinet, but they don't really know how much is out there. So you go and start looking at those cabinets, and all of a sudden you're probably over the 100 meter limit pretty quick. Next, and probably the very important, is cable separation. In other words, do you have any AC/DC? Okay, I'm not talking about the band. But they did have an album that applies here. I think it was called, what was it, High Voltage? Or perhaps you have multiple voltages that are high. In this case, it's imperative that these are the proper distance away from your PROFINET cables. Now, and probably even more important than that tip is we have for the topologies is a plan for correct grounding and shielding of the cables and the equipment to protect against electromagnetic interference. This is a really common problem that is often overlooked during design and installation. And if motors and drives are used, this is even more critical to properly shield those types of components. EMI can come in from a lot of different sources nowadays, such as lighting, your HVAC system, and even other ways. So everyone, please write a note to yourself. If an issue like this occurs, it can be darned expensive and really hard to isolate in a poorly designed system. I mean, red lights will start flashing, but nobody knows where the red light, what's causing the red light anymore, because it's a lower level issue, and those noise issues are really hard to track down. So please, to help with that, we have a functional earthing and shielding guide where you can get more details about this that I would highly recommend. Another aspect you should consider for topology design is to use managed switches. And we used to have a colleague who used to say, you will use a managed switch or wish you had. And I'm going to go a little bit further to say, in addition, a lot of these managed industrial switches are available, can also support the PROFINET protocol. And that can provide even more diagnostics in case of a network or even a device issue or failure by passing diagnostic information directly to your I/O controller or the PLC. And there's multiple manufacturers now or vendors that offer PROFINET switches and the capability to do that if you need an external switch. Again, some of the devices already have that PROFINET switch built into the device, but if you're getting external switches, we would recommend either a managed one or a PROFINET switch, which has been certified too. The last reason, and the most unique, is probably I wanted to mention, is the device replacement. This is an easy way, for example, if you have a device fail on your network, these switches can allow you to replace the failed device without having to have any kind of configuration information in the device. In other words, you pop a device in there with no name, no IP address, and the controller will automatically bring up the device. And it makes it really easy for device replacement or commissioning if you have those types of switches in the network too to help with that. Okay, we made it to our final slide on the topology tips. We already mentioned the IRT topology diagram and that those devices need to be interconnected, so we got that there. We also mentioned about media redundancy components are required. If you want to do a loop on Ethernet, you can't do it without those. And so you're going to have those components, those additional components or features in your devices or switches. Regarding network analysis, since we're doing a lot of switched Ethernet with PROFINET, the switches basically forward the traffic between the devices using the Ethernet MAC addresses. So if you try to plug your PC in and want to capture traffic for diagnostics performance reasons, you can't do that with just a straight connection. You have to have a switch with a mirror port or network tap to basically copy that traffic from the controller to the devices, and then you could view that with an Ethernet sniffer or network diagnosis tool. These types of devices or test tools are available from multiple suppliers and also often a feature on a managed switch supporting PROFINET too. So if you're looking for that, you want to get that. Finally, another important tip on topology is to document, of course, your network topology and the components that are out there, all the details, what kind of cabling you have, distances, and in addition, you probably want to perform a self or professional network validation when you're bringing your network online. If your network comes up okay, you did it right probably, and you need to say that kind of your baseline, if everything's working good. And if you have a problem in the future, something goes faulty, then you could take the new characteristics of the network and compare that with your baseline network, and then you could maybe determine if something had changed. Okay, so that finished up the topology section. Now I wanted to talk about some performance considerations for PROFINET design. So During this section, I wanted to take another closer look at network load and also talk about planning for your I/O cycles for the devices in the controller. And finally, more tips about the line depth. So we said we could have critical network sections where you have a lot of traffic converging, or you have chatty devices on your network, such they're using TCP/IP, again, such as HMIs or SCADA systems or other types of devices. So the network load should be estimated prior to your network install, part of your design phase, or at least checked before the network is put into operation. So PI recommends that the network load on PROFINET systems be between 0 to 20% on your critical points for ideal conditions. If you're above 20% on a section, then you're going to probably need to look at some of the topics we're talking about next, which will be your I/O cycles, your network layout. You might need to add or change some components. Maybe you're overloading some parts of your system, and check those things per the design guideline that we have. Finally, we do not recommend going above 50% network load. If you have that, these higher loads may cause you to get dropped packets or resource issues and delays on your network components through your switches or in your devices themselves, to where it causes delays, and we don't want delays out there in an automation system. Another tip on this network load is here. In case of multiple controller applications which are talking to their own devices, try to distribute the traffic evenly to avoid cross traffic. For example, you can see in this diagram we have right now, we've got a line topology, and we've got I/O controller 1 talking to its I/O device, and then we got I/O controller 2 talking to its I/O device, and they're kind of they've got the cross traffic over that line. So it would be better for communication layout to place the first I/O device again closer to the controller, pretty much near, so we don't have that cross traffic through the switches. If that's not possible, then you need to probably look at the update time and set that to a slower rate on the I/O device. And so speaking of update rates and planning I/O cycles, so when it comes to planning these I/O cycles for the devices, each PROFINET controller has a minimum SIM clock value, and that's typically going to be 1 millisecond. You can adjust it on some controllers, but most of the time you're going to stick your controller in there, and it's probably going to be 1 millisecond on your PLC. In addition, each I/O device has a minimum time possible that comes in with the vendor GSD file, the device description file that you get with the device. They're going to have a minimum update time in there. Now, when you're setting up these devices in the engineering tool, typically the engineering tool is going to pick the minimum times in the tool automatically. But we find sometimes this may not always be the best idea or optimal for your network. So for example, what happens if you pull in 64 devices in your configuration, and now the tool automatically sets all of those 64 devices to update at 1 millisecond? So the question is, do you need that for your application? You really need to check and adjust the update time if necessary on the devices based on your actual application requirements in the topology. For example, let's say we got a device that we set up at 1 millisecond. That means that device is going to be sending 1,000 packets a second. Now, again, granted, the PROFINET telegrams are going to be a lot smaller than you would have a TCP/IP message. But if you get a lot of these small messages, again, that can increase your network load. So if we changed our device from 1 millisecond, we say, okay, we don't need this device to run at 1 millisecond. We can set it to 4 milliseconds. Well, now it's only going to send 250 packets a second. So you can see you can reduce the load by looking at those things. So you can see, basically continue our train of thought on this subject, shown on this diagram is the network load in percent on the left-hand side compared to the number of nodes we have, and then the update times that we picked in the engineering tool. And you can see as the number of nodes increase, our network load is also going to increase, and if we use high, fast update times, then the load's going to increase even more. So that's important tip, to take a look at that update time when you're setting those devices up in your engineering tool if you've got a lot of devices, and especially if you've got line topologies too. So we want to talk about that. So each switch you have in your network is going to add a minimum delay as it goes through the switch to the communication. And if you have those line topologies, that can add up as the frame has to go through every switch. Now we have two main industrial switch types. We have cut through and store and forward. So it's up to the vendor of the switch again when you're getting it to determine which one you have. Now PROFINET RT can use either switch type, but IRT is always going to be cut through. So cut through switches basically forward the message on through without checking it till it gets to the end node. Store and forward will store the message, check it, and then forward it. So store and forward is a little bit slower than cut through when it comes to your forwarding mechanism. So one thing to note is the update time for your PROFINET devices and the switch type you're using can affect your maximum line depth, okay? So if we look at this table from our design guide and we go back to the example that I mentioned earlier, we had configured 64 devices in our engineering tool at 1 millisecond, and we were going to go ahead and download that controller, start it up. Well, it just so happened we had a line topology in this case, let's pretend, and if we were using store and forward switches, you can see that wouldn't work because you can only have a maximum of 7 in a line. So in this case, we would probably have to have some distribution switches, and we would only be able to go a maximum of 7 hops from the controller to the device. However, if we were using cut-through switches or IRT, which already has it, then we would see that we would be okay because we could have 64 devices at 1 millisecond. So that means we could run all those switches through, and that would work. So keep in mind, update time and switch type should be investigated when designing the system and looking at your line sections of your topology. Now, to help with the network design, there are a variety of tools available. Some are free, some are commercial, which can help in the process. PI offers a free network load calculation tool, which lets you estimate the PROFINET load on one controller at a time. And you can adjust for the number of devices, your update time, and so on. And that only considers the PROFINET protocol network load. It does not consider other types of traffic, such as TCP/IP or other types of devices that you might have out there. So other standalone tools will offer the best results on that, as they'll let you estimate not only the PROFINET load, but estimate load from other types of those TCP devices we talked about, like HMIs, IP cameras, vision systems, SCADAs, and other types of devices. And then you can get a good calculation on what your load's going to be at those critical points without having to go out there and start installing and then find out the hard way later that you've got these problems. It should also be noted that some PROFINET engineering tools will have a subset of some of these PROFINET design features in the tool. So as you're adding devices, or you have maybe like a topology view, it'll automatically kind of calculate what the maximums and minimums can be, and if the topology is going to work. So usually if something's wrong, when you compile your project, you'll get an error warning that'll say, we have an issue, you have too many devices in this line topology for this particular update time, so you might get a warning. So next, let's cover some tips on device parameters, what you should think about when you're designing your network. So one thing to note is all PROFINET devices are going to have a MAC address, an IP address, and a name. So we use the name to make it easy to manage your network. You can use different IP classes for your IP addresses, A, B, or C, A being the most nodes per network section, to C being the least nodes per network section. And you can also adjust that even further by using the subnet mask or network mask to break it down even more if you need to. If you need to get into that, you can check out some tools online like IP addressing or calculation tools, so you can get to kind of calculate what you want to use for your ranges for your IP addresses. So next, I've got some tips we should think about when it comes to naming and addressing our devices. So one thing about the device name is that this can be used for management and diagnostics. So if you make your device name meaningful, it can really help you if there's a problem. For example, if I've got a filling machine, I could call it just filler if I wanted to. Okay, it gives me a little bit of information. It's the filling machine, but I could expand on that if I want to. I could say it's the filler. It's in Josie. Okay, I'm in Johnson City, so I know Josie's the short for Johnson City, and I could say it's in cabinet 1. Or if I want to even get it more extravagant, I could put the IP address as part of the name. So now I've got the name of the device, the IP address of the device, where it's located exactly in the name. So if I got a diagnostic event, that would pop up in the diagnostic buffer of the PLC that we have the error coming from this filling machine at this location, and we get some information. You want to use correct naming conventions in your names. So we use the same naming conventions as like a web address. So it's a DNS qualified, what they call a fully qualified domain name. So you could use labels like 0 to 9, A through Z, dot or dash. And there's a few other criteria, but that's the main ones. Of course, label your devices out in the field with their name and IP address. Put the labels also on your network topology diagram, so you've got them there. And if you don't have the MAC address there on the device, you probably, which most of the time on PROFINET devices, the MAC address will be stamped on the device. But if it's not there, you probably want to put that out there too. Of course, work with your IT department if you have to on the IP address ranges. Typically for PROFINET, Class B or C is typically used because that's usually enough for the PROFINET network unless you're getting into really, really large networks. Keep in mind that most PROFINET devices will automatically get the IP addresses from the controller based on the configuration and using what we call the PROFINET DCP protocol in PROFINET. We don't really use DHCP because that's dynamic addressing. That's optional. Some devices may support it, but most of the time they're going to get their IP address from the controller. So again, that's a discussion you probably want to talk to your IT department about to say, what are we going to use for the ranges out the plant maybe versus the office? Because as we know, duplicate names and IP addresses are not going to be permitted. So if you're interconnecting a bunch of devices and in the office too, you got to make sure you don't have any duplicates of the names or the IP addresses. Okay, next I just wanted to finish up with a few special design aspects and applications we should take a quick look at in case you're doing some of those. Fast startup is a special application if you want to bring up a device quickly, and if you're setting it up, a lot of times you're going to disable the auto crossover functionality on the device. If you do that, that means you may need crossover cables, so you'd want to put that on your diagram and make sure that you get those correct cables, otherwise you're going to, maybe the device wouldn't come up because you didn't have the right cable. When it comes to wireless, we do, again, as Nelly said, support different wireless functionalities, Bluetooth, Wi-Fi, but that's a different type of network. So we can't run at the same update times as you would expect on a copper, or fiber network. So you're going to probably have to reduce your update times. In addition, you probably want to do a site signal analysis and survey to ensure, again, that you're not getting interference from IT or other signals. When it comes to topology diagnostics, if you're going to do that, make sure your software supports it or you're using the appropriate diagnostic devices for that. For that simple device replacement feature we talked about or commissioning, you want to have those switches with the PROFINET support throughout, and also your controller needs to support that feature. For motion control, of course, check for the appropriate components based on your requirements, whether you want to do 1 millisecond or 31.25 microseconds. You probably want to make sure you've got the correct components for that. And in addition, if you're going to be doing MRP or MRPD, excuse me, for IRT, you'd want to ensure that the devices had that feature. Finally, for high availability systems, you are going to remember that you need the extra cabling and the connections. And one other tip on that I wanted to mention, you don't want to close the loop until you've actually configured the devices to be in a loop, and then you can close the loop. If you close it too early, that's going to just cause the network to pretty much shut down. So you don't want to close it too early until you've configured it and set it up. Connection to higher level networks, of course, this is happening a lot nowadays because we have the office, we have the cloud. Anytime we're doing that, we of course want to consider security and the communications between the office network into the industrial network. So in this case, we probably want to use industrial firewalls to block anything coming into our network that we wouldn't want coming into our network. As well, we want to maybe look at what information we have going out and how we're sending that information. Maybe we need to encrypt it or do more secure channels if it's important information. So that's all I had for today. Let me hand back over to Nellie for a wrap up and conclusion. Back over to you, Nellie. Thanks.
Thank you, Hunter, for all of that information. I hope we were able to cover most of the topics that all attendees were expecting in this design webinar. Let me just finish up with a quick conclusion. We actually have a couple of slides here. Mostly what we wanted to say is that design is part of completing a PROFINET project. It is a key step. If you're not familiar with the technology, if you're not familiar with PROFINET, we'll really encourage you to start by not only learning about individual products, but also learning about the protocol. Then you can focus on devices and the design process. There's definitely some overlap between design, configuration, installation, even commissioning and maintenance. You may have noticed that some of the topics that we covered were related to configuration or even installation. There's really no hard and straight lines in the PROFINET project process. Well, in conclusion, designing and engineering a PROFINET project is really straightforward, especially if you already have field bus experience. PROFINET offers this modular approach to automation. It is flexible and versatile. There's no need really to utilize every single feature that PROFINET offers. We are aware that PROFINET offers a wide variety of features, but we do really always recommend to start slowly and build from there. Start with a basic setup and build on all the features that you would like to add later. Let me give you a couple of resources before we finish up this webinar. First, the PI North America website, if you haven't been there, is us.profinet.com. We have a lot of resources, including the webinars, trainings, blog posts, white papers. Please check it out. We also have several certified network engineering courses. If you enjoy the webinar, maybe you have been to our PROFINET one-day training classes, but you would like to go a lot farther and actually get certified. That is a great opportunity. I've also included the link of the PROFINET Design Guideline and tool. Again, this webinar was mostly based, about 80% of the content came from those design guidelines. They're very in-depth materials. They are made for engineers, by engineers, and they're a great starting point before you start into an application. We also have a couple of blog posts about designing, bringing Ethernet to the plant floor, and finally, the webinars URL, including this one and also a previous one that we actually did last year on PROFINET installation. So if you think you want to fill in some gaps, especially related to cables, connectors, cable routing, all of that information have been covered in the PROFINET installation webinar. About those certified network engineering classes, here is more information. We have those classes for Profibus or PROFINET users. They are very challenging courses. They're a full week training that is usually held in Johnson City, Tennessee, but we do go to our locations sometimes. The certification actually requires you to pass both theoretical and practice exam. We always say it's something like going from 0 to hero for Profibus or PROFINET, and you, upon completion and upon passing both exams, you will actually be listed in the certified network engineering list at the profibus.com website, and you'll be there for life. You can learn more on this URL and register online. You can also send us an email if you have any questions. We have some upcoming days this year. Now is kind of the time that you have been waiting for the Q&A. If you would like to ask us a question, I got a few there in the presentation that I have been writing down so we can answer them for you. But if you have any others, please type them. We'll try to answer as many as we can before we run out of time. All right, I got a couple right here. At first, let's go over this one first. Hunter, I don't know if you add some information into this one, but someone is interested in learning about any limitations for cable length, copper or fiber, and how to avoid those limitations, or maybe like higher length.
Cable length? Well, typically the copper. Okay, so can you hear me? Okay.
Yeah, I think the audio is good.
Okay. So typically on copper connections, we have a limitation of 100 meters. Now, if you're using, again, if you're going through like cabinets like with bulkhead connectors, or if you've got couplers and other things like that, it might be shorter than that, but that's typically just the standard for 100 megabits is 100 meters. And as far as same, I think for a gigabit. As far as fiber, it really depends on what type of fiber you're using, whether it's plastic or glass or PCF. And again, splicing in there could cause you to have some shorter runs. So I'd recommend, if you want to get more information about that, to again look into the guidelines and the installation guidelines to get the actual details. For example, I'm looking here right now at the maximum fiber path for POF in the guideline, and it says it's 50 meters. It says PCF's 100 meters, multi-mode glass is 2,000 meters. Again, we've got all those details inside of the design guideline that they can look over.
Yeah, and I think we mentioned a couple of different, types of fiber or copper. Yeah. So it kind of depends in which one, but 100 meters is kind of like a rule of thumb, copper and fiber, it kind of depends.
And then we have wireless, which also, depending on what wireless you're using, could be, and what kind of antenna you're using, you can have different distances for that as well.
All right. Well, we have another question right here, which is about switches. If PROFINET requires specialized switches on its network.
PROFINET does not require specialized switches. You only need an industrial switch with 100 megabit full duplex. That's the only requirement. We only say that you should try to use the switches with a PROFINET protocol capability, because again, you get a lot more diagnostics to your user application.
Yeah, it does help.
And of course,
diagnostics and commissioning.
Yeah, and the only other caveat is if you're doing IRT, you would need and had an external switch, then you would need a switch that supported IRT, the motion control. But that's really the only requirement. But most folks use a managed switch or a standard, industrial Ethernet switch with PROFINET. That's fine.
Yeah, we actually have a couple of articles and I think a white paper talking about how you can literally use a Best Buy switch, so something that you just buy off the shelf. If it's 100 megabits per second, full duplex, you're all set.
Right.
Another question right here. This one is about redundancy. How do you achieve media redundancy?
We use there's different ways you can do it. Some vendors have proprietary methods, but from the PROFINET standard, we have what's called MRP, Media Redundancy Protocol, or MRPD for media redundancy for planned duplication. That's for your IRT systems, and you pretty much pick one of those depending on what your application requirements are. And then you, of course, need to make sure that the components in that ring all support that topology. And that's often supported by both the I/O controller and the I/O device, as well as many of the PROFINET industrial switches will support the MRP capability, to where you can put your network in a ring topology. Of course, PROFINET also, process application can also support rapid spanning tree protocol. Some of the switches will support rapid spanning tree, but that's more of a, mechanism that came from the office, so it takes a little bit longer for recovery. MRP recovers in like a few milliseconds. MRPD is bumpless, and then Rabbit's Pantry takes us some seconds to recover. So it depends again on how quick of a recovery time do you need for your network to come back into operation if there was a fault.
All right. Yeah, and if the attendee that submitted that question could just stay online a minute after the presentation, I could send them a URL for a white paper that talks about all about redundancy. So that could help a little bit more extend that. We also have another question right here. This one is a bit of product specific, but maybe we can give some insight there. Is there any vision systems available with PROFINET interface?
Yes, there are multiple vision systems that have PROFINET capabilities. They can probably go up into the PI product finder. So there's a product, you can probably tell them about that, Nelly.
Yeah, so in the ProfitBus,
we have the product finder.
Yeah, in the profitbus.com website, we have a product finder. If you're able to find that site, which I can send the URL in just a minute, you'll be able to search for a variety of products. And I'm sure if you put a vision system, a few will pop in there. It's not 100% of PROFINET products are, because manufacturers usually have to list them on their own, but their own to the list. But I think a good number of them are there, and always is your best friend. So if you were to search them PROFINET, I'm sure a few will come. Let me check if any other questions coming in. I think maybe one more related to switches. I know, Hunter, maybe if you can help me clear these doubts from a couple of people. They were saying if you could refresh on which one is the difference from a managed and an unmanaged switch.
Well, I mean, an unmanaged switch, of course, comes with there's the LEDs on the front of it, and there's no management interface like a web page or a console that you can go into to make any adjustments on the switch. So unmanaged switches are cheaper, but they don't provide much diagnostic capabilities, which we probably would want on the industrial network. So I mean, pretty much all that you have for the diagnostics on an unmanaged switch is a green LED or a flashing amber LED, and that's it. And if something's not working, you can't really tell because it's still probably going to have a green LED. So we would recommend, again, a managed switch, which is going to have a web interface or some kind of console interface, and you could go make adjustments on the switch, maybe make changes. You're going to have network statistics in the switch probably with SNMP. So a lot of those managed switches also will support some of the redundancy mechanisms, and that way you can get more diagnostics for your application. In addition to managed switches, if you go one step further, you can get a PROFINET managed switch, which also not only acts as a switch, but it also supports the PROFINET protocol, meaning it has a GSD file, and you would bring that switch into your configuration, and then you can do a lot more things with that too to get diagnostics directly to your PLC application.